Okay. So Bernoulli example, if we wanted to do one, I call this draining the tank. This is a very common kind of problem you'll see in books. What I don't like about draining the tank is that it's got sort of an approximation in it, but I'm going to show you exactly where the approximation is. Okay, we're going to do it without the approximation, and we're going to see, okay, this is why they do that. But it's such a common thing that comes up, I think it's worth talking about. Okay, so we have a tank, right? It has radius big R. Okay, it has a hole in the bottom. There's a hole in the bucket, dear Liza. Does anybody know that song? There's a hole in the bucket? Okay, good. Okay, I don't have to sing it then, thank God. Okay. Tank, hole in the bucket, dear Liza, and the water flies out like that. All right. So the tank, the big tank here has a big radius R. Again, I should not start singing songs and phrases from my youth, probably. And no more candy stripers. Hole, radius R. Right. Radius R. And the liquid is, the hole is H below the liquid. H below liquid surface. All right, so this is H here. There we go. And Y above the bottom. Okay, so radius R, hole radius R, H below the liquid surface, Y above the bottom of the tank. All right, so this would be Y. There we go. A hole is sitting Y above the tank. And what was the question? Let's see. And the tank is at P. The tank is held at P. So the pressure up here, we're saying, the pressure here is P. So it might be open to the air, it might be closed and sealed, and the pressure is set at some value, whatever. The reason this is a popular kind of problem is this could be a fire extinguisher. We have high pressure here. This could be an open tank where you're just asking how long will it take all the water to leak out. We're going to do this as an IV bag for a transfusion. Okay, you get the idea, not as a demo. Okay, so then we're trying to solve for, I forgot what we're trying to solve for. Yeah, how fast does the water come out? How fast does the water come out? In terms of all these given parameters here. Rho, H, yada, 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 yada. Okay, here we go. So we're going to apply Bernoulli. And the key to applying Bernoulli is pick 2 points. So in an energy problem, you have like the initial and the final. In Bernoulli, you pick 2 points in the flow, and you say that thing must be equal at those 2 points. All right, so the way I'm doing this in my notes is I have, this is point 1, right at the top of the meniscus, and where it's flowing out is point 2. Okay? So we're going to equate Bernoulli at points 1 and 2. All right. See if I can not screw this up here. Let's see. Okay. So what is the pressure at point 1? All right. So we're going to say 1 equals 2. Here we go. I'm going to write nice and big. The pressure at point 1 is P. Whatever we wanted the pressure to be up there. Different kinds of problems. If it's open, it's atmosphere. Who knows what it could be. But it's some pressure. Right? Plus the density of the water, you know that, rho, gravity, you know that, and then the height of that point, and you can see it's at h plus y. Now you can kind of maybe tell that this term is kind of like a potential energy term, isn't it? Right? So it kind of, you would think, maybe it doesn't matter where 0 is. And you're right, it doesn't. Right? But let's just put h plus y anyway. Let's pretend we're very normal people who say that y is 0 here. Okay, P plus rho g height plus 1/2 rho, and now what's the velocity there? I don't know. Call it V1. V1 squared. There's an unknown. All right? Our first unknown. We're looking for V2, but apparently we don't know V1. Okay. So let's say that now equals 2. Okay, what's happening at 2? Okay, this is a little weird. The pressure at 2 is atmospheric pressure, because we're talking about outside the hole. Okay? P, I'd say that's the only really ambiguous thing about solving this problem, is to know that you put atmosphere there. And then it's sort of a rule you just have to follow, or let me try to physically explain it to you, okay, real quick. I'm saying it's atmosphere because really what happens is most of this water isn't moving, and there's some streamline, right? There's some streamline that's going out of here or something. But really the velocity of this big thing is very small compared to this thing. So you sort of imagine that it's not really moving here. Because if you did sort of a static pressure calculation, you wouldn't have atmospheric pressure here. It would be higher than that, right? If I just said, what's the pressure here? You'd say, oh, it's P at whatever here, atmosphere, plus rho GH, or whatever it is. But no, so that's why we're not saying the pressure here, we're saying the pressure out here. Out here, it's atmospheric pressure. And you might say, well, but there's a little flow of water. Maybe that creates more pressure. And the answer is no. We're doing this ideal thing where the pressure's high here and the pressure's low here. And that's why the water flows. Yes, if you micro zoom in into the little tube that is the hole in the wall, there would be like pressure gradient across that little hole. Right, but we're just treating this as a thin hole. The pressure in here is some value, the pressure out here is some value. Okay? So hopefully that helps a little bit, but if you're ever doing this problem, just know that the water is flowing out, and you're asked how fast it's flowing out. Even though there's water flowing out, even though it's moving, it's still under atmospheric pressure. Okay? That's the only ambiguous or tricky thing, I would say. Okay, now we need the rho GH term. All right, so rho, density of the water, G, you know that. How high is the hole above what we're calling 0? Y, the thing we called Y. Somebody asked, is this a closed container? I'm saying it could be either way. I'm just saying there's a pressure up there. Don't worry about it. Right now I said P. I didn't say it's at atmospheric pressure, so it must be closed. Okay, but we'll open it in a minute. So I'm going to put a Y here, okay, because this is sitting at Y. And then plus, let's speed it up here, rho V2 squared, another unknown. Oh, that's actually the one we're looking for. We're looking for V2, aren't we? Yes. Okay, so now we get to start simplifying, okay? And I've told many people about this intro physics, as everybody thinks you have to have had calculus. And the answer is no, you don't have to have had calculus. You just have to be really good at algebra, right? So people that have had calculus tend to do better. It's not because of calculus. It's because they're fast at algebra. Like, you know what I mean when I say, oh. Right? You know what I'm saying? Okay? If you can do that immediately, you'll go through this problem fast. If you got to think about that for a while, that's okay, but it'll slow you down. You see what I mean? This distributes to both of these. This is rho gy plus rho gh. Therefore, we have a rho gy added to both sides. So I cancel the rho gy there, and I just cancel the y there. So I know you get that. I'm just saying this is the thing that slows people down. So we simplified. We got rid of. We realized it doesn't matter why, right? We could have called the hole 0. It doesn't matter. All that matters is the difference in height between the hole and the surface on the top. Right? What else do we know? So now our problem is we have one equation and two unknowns. Right? So we need another equation. There's only 3, right? There's only 3 equations here. And we need one with V1 and V2 in it, right? It's clearly the second one, continuity. So we apply continuity equation. We say, okay, well, the area at the top, so A1 V1 equals A2 V2. And we know what the A's are. They're pi r squared. So at the top is the big R. Pi big R squared V1 equals, and the bottom is the little r, pi little r squared V2. Okay? So now, how good are you at algebra again? I'm solving for V2, so I should probably plug in for V1 and get it in terms of V2. Right? That would be more efficient than solving this whole thing for V1 and plugging it back in here, right? That would be bad algebraic hygiene. Yes? Oh yeah, so the hole has a little teeny radius here. So here we cover the radius of the hole, and there, so we're right on the outside of the hole. Yeah, we're really technically, mathematically thinking about the outer surface of the hole, of the container. And it has a radius little r. Okay, anyway, so then we just solve this for V1, And you see that V1, the pi's cancel, it's little r squared over big R squared, V2, right? So you say, okay, and then you get rid of this, and then you blank that out, that. All right, let's keep going. Let's bring this home here. Solving a problem. I love solving problems. Okay, so what are we left with then? We've got the P is still there. That's a known. We're fine with P. We've got rho GH. It's all known. We're fine with that. We got 1/2 rho, and then we got to plug in, V1 squared, but that's R squared over R squared, V2 squared, or V2, rho little r over big R to the 4th, oh my God, V2 squared. All right, so the V has the R squared because it's area, but then we're going to square the V, so it's actually to the 4th power. Interesting. I haven't seen anything to the 4th power since I made these notes 30 minutes ago. Equals, now let's do the other side. Atmospheric pressure, where the hole is, we got rid of its rho GH plus 1/2 rho V2 squared. Right? And there's our V2 squareds right there. So here's our unknowns now. V2 and V2, because we're really good at algebra. Yes. Okay, now we've got to get really good at algebra. Okay. So now we're going to multiply by 2 and rearrange. Again, you got to be good at algebra and know, oh, I can multiply the whole equation by 2. That'll get rid of the halves. It'll bring in 2's, but I'd rather have 2's than halves. That's just the kind of guy I am. So if I do that, I say, let's see. Oh, I'm probably just going to copy it off of here. Let's see. 2's and rearrange. Okay, so what we're going to do is everything by 2, and we're going to bring this over here to get the V2's on the left. So we're going to be left with rho V2 squared. And what would that have to be multiplied by 1 over there, and then bring this over minus R over R to the 4th. Yeah. R over R to the 4th, right? So that's all the rho V squared right there. Brought that over there, multiplied through by 2, and then everything left is going to have the 2 on it. So that went over there, so this is over here. So it's 2 times whatever that pressure is minus the atmospheric pressure. And then this little pathetic thing sitting here, plus 2 rho GH. Plus 2 rho GH. Interesting. Any other algebraic conveniences here? Oh, no, there are none. Sorry. I thought there was one. Okay. Now let's just solve for V. Okay, so I'm going to bring the rho under there, bring that big nasty mess under there, and write an equation for V. Here we go. Hold on to your hats here. A big square root, that's never a good sign, over 1 minus R over R to the 4th. Right, that's in the bottom. And then we have 2 times P minus P ATM over rho. Right, la 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 over rho. And then we have plus 2GH. All right, there it is. The leaking container problem. I'll dub in the applause. Okay.